Hello friends, continuing with the topic of electronic devices, in which we were studying junction diode. After having understanding of PN junction diode and its applications, today we come to special diodes, Zener diode and avalanche diode. Today's topic is Zener diode and avalanche diode. So first we take up Zener diode. Step by step we will try to understand what is Zener diode. First we take up construction. It is a PN junction diode. What is the construction? It is a PN junction diode. Basically all diodes are PN junction diodes. Now doping levels. Doping levels are very high, P++ and N++, resulting into width of depletion layer very small, of the order of 10 raised to power -7 meter, such that a very small PD applied across the junction generates very high electric field across the junction. For example, applied PD is suppose 6.3 volt, then electric field across the junction would be E is equal to V by L, where L is width of depletion layer. So therefore we have 6.3 volts divided by 10 raised to power -7 meter, which comes out to be 63 into 10 raised to power 6 volt per meter. That is 63 millions volt per meter. So it is a tremendous electric field applied across the junction when we apply 6.3 volts as PD across the junction. Okay. Third, circuit symbol. This is the circuit symbol of Zener diode. A node has the same drawing, but cathode has a different drawing. The vertical line of cathode has been curved at both ends. So therefore it forms the symbol of Zener diode. Fourth, biasing. How we give biasing to Zener diode? It operates under reverse bias conditions. Here you see in this circuit, a node is connected to negative terminal of battery, cathode is connected to positive terminal of battery. So therefore this diode is reverse bias. So this Zener is reverse bias diode. Now fifth, operation of Zener diode under reverse bias conditions. Now when reverse bias increases from 0 onward, initially a very feeble current of the order of microamperes flow through the junction due to minority carriers, because reverse bias acts as forward bias for minority carriers. As reverse bias is increased further, say to 6.3 volts, electric field across the junction would be 63 million volts per meter. Due to this high field emission of electrons takes place. Lattice electrons leave their places and start tunneling through the junction, resulting into a large current to flow through the junction. I repeat, when reverse bias increases from 0 onward, initially a very feeble current of the order of microamperes flow through the junction due to minority carriers, because reverse bias acts as forward bias for minority carriers. As reverse bias is increased further, say to 6.3 volts, electric field across the junction would be 63 million volts per meter. Due to this high field emission of electrons takes place. Lattice electrons leave their places and start tunneling through the junction, resulting into a large current to flow through the junction. Okay. Now, sixth, IV characteristic. IV characteristic of Zener diode is as shown. Look at this circuit. This circuit is of Zener diode, which is having 6.3 volt as Zener breakdown voltage. So 6Z3 means it denotes its breakdown voltage 6.3 volt. Okay, so this diode is reverse biased and bias is variable. This arrow shows that bias is variable. We can vary it from 0 onward. Now let us define Zener voltage and Zener effect. First we take up Zener voltage. What is Zener voltage? The voltage at which junction breakdown takes place and reverse current shoots up is known as Zener voltage, and the effect itself is known as Zener effect. Okay, now look at the characteristic. Now here Zener breakdown takes place, that is, a reverse current shoots up. So this voltage is known as Zener voltage, and the effect of breakdown of junction is known as Zener effect. Second, avalanche diode. First, construction. It's a PN junction diode, because you know all diodes, all semiconductor diodes are PN junction diodes. The difference is of doping levels. Now second, doping levels. Doping levels are very high, P plus and N plus, a little less than Zener diode, where we have in Zener P plus plus and N plus plus. 3. Circuit symbol. This is the circuit symbol of avalanche diode. We draw the circuit symbol of Zener diode and write AV. AV means avalanche diode. It becomes avalanche diode. Biasing. It operates under reverse bias conditions. Here we have applied reverse bias to avalanche diode, which is 24 AV3, means its breakdown voltage is 24.3 volt, which is very high as compared to Zener diode of 6Z3. Now operation or working. When reverse bias increases from 0 onward, initially a very feeble current of the order of microamperes flow through the junction due to minority carriers, because reverse bias act as forward bias for minority carriers. As reverse bias is increased further, minority carriers are accelerated and collide against atoms and ions of the lattice, knocking out electrons. Thus, number of electrons increases. Now here is the difference between the principle of Zener diode and avalanche diode. On further increasing the reverse bias, electrons are further accelerated and knock out more and more electrons. It becomes now difficult to differentiate between minority electrons and others. At a particular voltage, all of a sudden an avalanche of electrons and holes comes in and start crossing the junction, resulting into large reverse current to flow through the junction. I repeat, at a particular voltage, all of a sudden an avalanche of electrons and holes comes in and start crossing the junction, resulting into large reverse current to flow through the junction. That is, junction breakdown takes place. Fifth, IV characteristics. IV characteristics is as shown here. Sixth, avalanche voltage. What is avalanche voltage? The voltage at which junction breakdown takes place and reverse current shoots up is known as avalanche voltage, and the effect itself is known as avalanche effect. I repeat, the voltage at which junction breakdown takes place and reverse current shoots up is known as avalanche voltage, and the effect itself is known as avalanche effect. Here at this point, this is avalanche voltage and A for avalanche effect. Okay. Now assignment 14 continued. Question number 37. Zener diode has higher dopant densities as compared to ordinary p-n junction. How does it affect, number 1, the width of depletion layer, number 2, junction field? Question number 38. Draw the voltage current characteristics of a Zener diode. Now third, applications of Zener/avalanche diode. In the first step, we have studied about Zener diode. In the second step, we have studied about avalanche diode. In the third step, we are to study about applications of Zener/avalanche diode. Now, Zener or avalanche diode are used as voltage regulators. Zener used for regulating low voltages and avalanche is used for regulating high voltages. I repeat, Zener and avalanche diodes are used as voltage regulators. Zener is used for regulating low voltages and avalanche used for regulating high voltages. Now, how Zener or avalanche diode is used as voltage regulator? Here is the circuit. So we take up step by step. First, we talk of circuit. RS is safety resistance. RL is load resistance. 9Z3 is Zener diode whose breakdown voltage is 9.3 volt. Input is 0 to 15 volt. Output is regulated 9.3 volt. So this is the circuit of Zener. So if you want to use avalanche as a regulator, then replace Zener by avalanche. Okay. B. Working or voltage regulation. Now let us discuss step by step. First, when input voltage is less than 9.3 volt, output voltage is equal to input voltage. Because Zener behaves as open circuit, so whatever is the input voltage, we get at the output voltage. Second, when input increases beyond 9.3 volts, Zener breakdown takes place and a large reverse current flows through Zener branch, which also flows through series resistance RS, and excess voltage drop across RS, and output is regulated to nearly 9.3 volts. I repeat, when input increases beyond 9.3 volts, Zener breakdown takes place and a large reverse current flows through Zener branch, which also flows through series resistance RS, and excess voltage drops across RS. Output is regulated to nearly 9.3 volts. Okay. Now C part, designing a voltage regulator. Given standards for designing are regulated output 9.3 volts, load current 40 milliampere, input variations from 9.3 volt to maximum 15 volts. Now let us see how we can design this type of regulator with these standards. Now second, selection of components for designing voltage regulator of given standards. Now let us take up step by step. First step, we need a Zener diode. Now Zener diode with Zener voltage 9.3 volts is required. Let Zener can draw a current of 100 milliampere safely. That is, the rating of Zener diode is 100 milliampere. Now this is the circuit diagram which we are to arrange. Now let us calculate first the value of load resistance RL. How we calculate the value of RL? Using Ohm's law, RL is equal to V by I. So V here required is 9.3 volt and load current is 40 into 10 raised to power minus 3 amperes. Therefore, it comes out to be 930 by 4, which is equal to 232.5 ohm. Now what should be the power rating of this resistance? Power rating is V into I. So we get 9.3 into 40 into 10 raised to power minus 3, which comes out to be 372 into 10 raised to power minus 3 or 0.372 watts. Now plus 25% for safe operation. So 25% is 0.093. When we add 0.372 and 0.093, it comes out to be 0.465 watts. Practically, calculated values are not available in the market. Practical availability of the component would be 222 ohm, 0.5 watt, which is very near to the calculated values, and it can be used for the purpose of designing. Now let us calculate series resistance RS. Now current through series resistance is equal to 100 milliampere plus 40 milliampere, which is equal to 140 milliampere. Now excess voltage drop across RS is 15 minus 9.3, which is equal to 5.7 volts. Therefore, RS would be equal to 5.7 volt divided by 140 into 10 raised to power minus 3 ampere, which is equal to 570 by 14, or comes out to be 40.7 ohm. Now what should be the power rating of this resistance? Power rating is equal to V into I. So we have 5.7 into 140 into 10 raised to power minus 3 watts. It comes out to be 0.798 watts plus 25% for safe operation. Now 25% of 0.798 is 0.1995. When we add 0.798 plus 0.1995, it comes out to be 0.9975 watts. So practically again, these calculated values will not be available in the market. So practical availability of the component would be 39 ohm and 1 watt. And we use these values for designing the circuit. Now fourth, list of the components to be used for fabrication of the circuit. First, 9Z3 more than 100 milliampere of current rating, Zener diode which can handle current more than 100 milliampere safely, because 100 milliampere is the load current. So the Zener should have current tolerance more than 100 milliampere. Second, load resistance 222 ohm, 0.5 watt. Third, series resistance RS 39 ohm, 1 watt. And then you assemble this circuit and test practically the inputs and output, make a data and verify how much is the variation from calculated values and the used values of the output voltage. It will be nearly approximately exactly the same as we have designed. Okay. Now assignment 14 continued. Question number 39. The output of an unregulated DC power supply needs to be regulated. Name the device that can be used for this purpose. Draw relevant circuit diagram. Question number 40. Explain with the help of circuit diagram how a Zener diode works as a DC voltage regulator. Draw its IV characteristics. Now, question number 41. Draw VI characteristics of a Zener diode and with a circuit diagram explain how a Zener diode can be used as voltage regulator. Question number 42. Design a voltage regulator for a regulated output of 6.3 volt and a load current of 60 milliampere using a zener of 6.3 volt, which can draw 90 milliampere of current safely when input varies from 6.3 to 10 volts. Thank you so much. Next time we'll take up photonic devices, which are photodiode and solar cell, and then LED and laser diode. Till then, goodbye and good luck to you.